Okay, I think we can begin with the second session of the Mag2Pol introductory courses. I'm really happy to see that I didn't scare you away after the first course, so many of you came back for more. That's good to see. I'm Navid Qureshi for those who participate for the first time, and I will be assisted by Edmond Chan today. Katie Beauvoir is not able to do it, to make it today. And for those who were not present last week, I would say we do it exactly in the same way because it worked rather well. So if you have any questions throughout the course, please type it into the chat, and Edmond will answer you directly in the chat or interrupt me, and then I will try to answer your question. And this session is again recorded, and I will put the recording on the Mag2Pol internet site. So if I could just ask you to switch off your cameras and microphones, that would be great. Okay, so let's start. I will share my screen. So I hope that worked. So last week, we were talking about the general use of the program and with some special focus on powder data analysis. Today, we will focus on single crystal data analysis, and I will show you how to introduce in different ways the magnetic structures into Mag2Pol. And next week, we will talk about polarized neutron techniques. And I'm very glad, proud, and excited to announce that there will be a special contribution by Francis Tasset, who is a pioneer in polarized neutron techniques, and he will give us historic insight on the terminology of spherical neutron polarimetry. So I'm really looking forward to this. And if necessary, we'll have a fourth session, and I have written that in red because that's a new date. It has been postponed to the 2nd of November, if we need it. This is what we're going to talk about today. I will show you how to introduce magnetic structures into the program. We'll see how to change the propagation vector, how to use basis vectors, and so on. Then I will show you how to introduce a particular magnetic symmetry, either by using irreducible representations, or IREPs, or by using magnetic space groups or magnetic superspace groups. Then we will move on to the single crystal related stuff, like the orientation matrix, which gives you the sample orientation in the diffractometer, or instrument definitions, which are important in that context. Then I'll show you how to build a three-dimensional model of your single crystal, which you can use for an appropriate absorption correction. Then we'll play with some real data. In a first step, we'll do a nuclear refinement on a multi-wavelength data set. And I'll show you the single crystal specific parameter scale and extinction correction. And then we will move to the more important step in this case. It's the magnetic refinement. And I'll show you how to discard models by trial and error. And I'll show you a co-refinement of single crystal and powder data. So I will now switch to the program. I will launch it. So last week, we didn't get very far in the description of magnetic structures. We started briefly with a monoclinic crystal structure with some random lattice parameters, and we placed a magnetic ion at the origin of the cell, which looked like this. And I arbitrarily set a spin component along the A-axis, which gave me a ferromagnetic structure. I also briefly played with the propagation vector. So if I enter a 1/2 here, you see that I can create an antiferromagnetic structure, which is doubled along the A-axis. And if I type in 1/3, you see we have a structure which is tripled along the A-axis. Now, the magnetic moments are calculated according to the propagation vector formalism. So what you have here are not directly the components of the spin, but these are the components of the Fourier coefficient of the Fourier expansion of the magnetic moment. So if you're not familiar with this, look it up in the manual or in other references. This is a very elegant way to describe complex magnetic structures, and it will let you understand how it happens that you have a smaller moment pointing along the other direction, because you have actually a wave which modulates the amplitudes of your spins. And it will also let you understand what happens if you have an imaginary component which is perpendicular to the real component. So this creates a rotation of the spins. And in this case, the rotation plane contains the direction of propagation. So by definition, this is called a cycloidal magnetic structure. And if your real and imaginary components are perpendicular to Q, then you have what you call a helicoidal magnetic structure or a helix. Now, these, let's say, more complex magnetic structures may benefit from some hints to understand what you're actually trying to express here. So in this context, I would like to draw your attention on the guides to the eye, which you can draw in 3D. So you can choose from a list of objects. And in this case, I would like to show where the propagation direction is. So I will choose an arrow and I will put it below the unit cell with a certain direction. Now I have the arrow here and I would like to add a text. I write Q in a font size which is a little bit more readable. And now I can show you this magnetic structure with the direction of Q, and I can rotate this around and you will always see it in the right direction. So it might be useful for your figures which you want to create. You can do some more fancy stuff like a spiral, and I will use the same components as for the spin. And I've played around with these values, so I already know what to put in there, but everything is very well documented in the manual. I can even use a color gradient. And now I have a spiral which shows how the tip of the moment rotates along Q. So that may be useful. You can even use some higher number for the windings to make it more dramatic. Now it looks like a phone cable here. So these are different options to facilitate the understanding of the structure. Then one comment on a new object, HKL planes. This was actually the idea of one of the participants last week. So now I have included this into the new version. So you can draw HKL planes to make it easier to understand how your diffraction geometry looks like. So I mentioned this. So if you have any ideas or suggestions, just let me know. And in general, it doesn't take too much time until it is implemented. So you have those HKL planes, which even grow as you use a bigger box. So it's quite useful. So now I will remove all those guides to the eye, and I don't want to delete them. So I just go to plot and unplot them. Okay. So let's go back to a simpler magnetic structure. I put the propagation vector back to 0, and we go back to this simple ferromagnetic structure with the moments along A. And I will add a second magnetic ion somewhere in the unit cell, random position, which looks like this. And I will place a spin component along the Y direction or the B direction. So something is wrong here. So we have 4 red atoms, but there's only 1 red spin. So something is missing, but this is normal because under the symmetry tab, we have given the program the information about the nuclear symmetry, but for the magnetic part, there's only the identity here. So we are missing some operators. Where can we get them from? Well, we can click here on this icon, space group tables, which will open a new window. And here we have different tabs, and we will stay on the first one for the moment, crystallographic space groups. So you can enter your space group here. You can choose it from these combo boxes, but we will stay with P2 over M. And the information is about the operators in the space group. So you have the coordination triplets, you have the symbol of the operator and its position, and you have the list of Wyckoff positions of that space group. The convenient thing is that the space group operators are generated in exactly the same way as in the international table, so you can directly compare them one-to-one. Okay, so now let's use some operators. Let's use the twofold axis and the mirror plane. So the twofold axis is expressed by minus x, y, minus z. And the mirror plane is x minus y, z. I could add the inversion, but I don't need it because actually what I'm entering here are generators. And by combining the second and the third one, it automatically generates the inversion. So I don't really need to add it. So if I generate my unit cell now, I have red spins on all red atoms. So I have a direct visual feedback that what I'm doing until now is correct. Although I have not entered any information about the magnetic symmetry. So I could actually play around with these values as much as I know. I'm just doing some random stuff here. So I would not really recommend you to use the manual input of magnetic symmetry unless you really know what you're doing. And even then, there are easier and better ways to do it. But it gives you a chance to understand how this actually works. You can play around with these components to see how this actually generates the magnetic unit cell. So for the moment, we see here, we have used X, Y, and Z components for the real and imaginary parts. You can also use basis vectors, which you can define over here. So if you click here, you can say use basis vectors, and then you can define basis vectors for all of your magnetic sites. You can say, for example, I want the first site to have a basis vector along the diagonal in the AB plane and another one along C. And for the second one, well, let's do exactly the same. And now you see how your magnetic structure differs because the first one, and you will see it as a tooltip here, takes the coefficient 2 times the basis vector, which is along 1, 1, 0. And for the second side, you have the coefficient multiplied by a basis vector which points along the C-axis. So that's a different way of entering magnetic components, spin components. But as I said, all this manual input, you really need to know what you're doing. So what I would recommend is to calculate the magnetic symmetry using, for example, irreducible representations. And the good news is that you don't need to create a new input file, run an external program, copy the output of that program into Mag2Pol. The only thing you need to do is to click on this icon, irreducible representations. And it will show you everything you need to know. There are some details about the operators in the parent space group and in the little group. Then you have a list of atoms. So that's a lot of group theoretical stuff, which where I won't go into detail because I could talk about that just for 1 hour. This is interesting. You have the decomposition of the magnetic representation. This means that for this site, there will be 2 IREPs or magnetic structure models, if you want, with non-zero basis vectors. And for gamma 1, there will be 1 basis vector. And for gamma 3, there will be 2 basis vectors. Whereas for the second site, which is less symmetric, we put it somewhere in the unit cell, we have 4 IREPs, and each of those IREPs has 3 basis vectors, which are in agreement or compatible with the symmetry. Here under the multiplication table, you have just some informative stuff for you to understand how the symmetry of your space group works. So you can see what happens if you combine the twofold axis with the inversion center. It will give you the mirror plane. And you see here at the bottom, if you click on those different cells, it will show you how the operators behave if you combine them. Then under IREPs, we have the table of our 4, in this case, 4 irreducible representations. They're all one-dimensional. You can see that it's just a +1 or a -1. For 2-dimensional representations, you would have a 2 times 2 matrix, and for a 3-dimensional one, a 3 times 3 matrix here. But let's keep it simple. And here you have the basis vector tab, where you can see the basis vectors for each of those IREPs. So as we have seen from the decomposition before, gamma 1 will have 1 basis vector. The spin can only point along the B-axis. And gamma 3, the spin can point along the A or along the C-axis. But for gamma 2, there is no allowed spin component which respects that symmetry. That's really valuable information because if you stick to a correct symmetry, you get rid of a lot of components which are actually not allowed by symmetry. And for site 2, you see that all the representations have 3 basis vectors, but they transform in a different way, as you can see, as the minus signs change from irrep to irrep. So how do I transfer those symmetries to my main window? Well, it's very simple. You just come to the irrep tab, you select an irrep, you right-click it, and you say use gamma 1, and you see it directly changed the magnetic structure. And I will use some random values for the 2 sites to see how the magnetic structure could look like. And now I can easily cycle through the different models, and I can directly see them in the main window. I would like to draw your attention on gamma 3, where we see that the 2-fold axis and the mirror plane has a -1 here. That means that those operators are used with the so-called time inversion. Those are primed operators. And from here, I can draw the connection directly to magnetic space groups, which is another way to introduce magnetic symmetry. So I could say, please use the magnetic space group, which is P2 prime over M prime. And if I generate the unit cell, yeah, that's not what I expected. I'm honest with you. Let's go back. Maybe I did not select gamma 3 in the beginning. So I select gamma 3. And now I check something here. And if I use P2 prime over M prime, now nothing happens because it's exactly the same symmetry. I could change the magnetic symmetry here by removing this prime, for example. Now it would be in P2 prime over M symmetry. And if I regenerate the cell, you see we have a different configuration of spins. And if I remove P2, the prime on the 2-fold axis, and I add it on the mirror plane, again, we have a different magnetic structure. And if you would like to use the magnetic space group, which is P2 over M, well, we have the same label already reserved for the crystallographic space group. And if you want to tell the program that it's a magnetic space group you want to use, you have to use the underscore here. And we get this, this structure. There is another way to assign magnetic space groups, again, by clicking on the space group tables. And now, since I have chosen a magnetic space group in the main window, it will directly go to the magnetic space group tab in this window using P2 over M. And again, you can choose among a lot of different magnetic space groups in different systems. It will give you the operators of the space group and the Wyckoff positions, but now you can also see it will give you the allowed basis vectors and how they transform from site to site. And you can see that for the more symmetrical side, there are more constraints. For the less symmetrical sides, there are less constraints. And I could go, or I can choose another space group here, and I can apply it by clicking transfer MSG. And now I directly have it in the main window. And I can even play around with the degrees of freedom I have within this symmetry. So this is great to understand what your magnetic structures could actually look like. And you can also play with the crystal degrees of freedom to see what your structure could actually look like. And you can reset those parameters. Any questions so far? Everything is clear? Are you still there? Okay. So this was a very easy example, and I would like to show you something a little bit more complex. So I will load an example, which is gadolinium manganese 2O5, which crystallizes in the PBAM space group. And from neutron diffraction, people have found out that the magnetic cell is doubled along the a-axis, which is expressed by a propagation vector 1/2, 0, 0. So in order to find out which magnetic space groups are compatible with these information, you can use other programs like MaxMag from the Bilbao crystallographic server. And I will show you how nice and easy it is to combine Mag2Pol with those results. So if you use MaxMag, this is the website. What you have to do is you choose your parent space group, which is PBAM. You enter the propagation vector. You submit. And now you have a list of maximal magnetic space groups for the information you have just typed in. And we will take the first one as an example. So I click on show here. And here I will get all the information I need to input into Mag2Pol. So to do that, I will open again the space group tables. And now I know from the first line already that I have to use the parent space group PBAM in a different setting, in a different basis. And the basis is 2ABC because the lattice is doubled along the A-axis. So I come here and say, okay, I need to use the basis 2ABC. You could also directly modify the transformation operator here by typing 2. So those two things here are synchronized. And now I transform the space group, and you will see how you go from PBAM with 8 operators to a different setting with 16 operators, because now we have added this non-primitive translation of 1/2, 0, 0. Now the other part is we use magnetic space group PACA21 or the numerical label 29.104. So I come here and I can do either thing, either enter the label or the number. I will do the number, which then will directly be transformed into the label. And I have to use this space group in a different setting, which is given by this transformation matrix, which I can directly input into Mag2Pol and the translation of the origin. And it will give you the transformation string here. And I transform the magnetic space group, which of course will change my symmetry operators. Now, all this stuff is correctly done by the BCS, but now this will actually help you to understand what it has actually done. So I will copy the information of the operators and I will just paste it below the ones of my parent space group to see what actually happened. So the program has made the transformations so that the magnetic space group is a subgroup of my PBAM space group, and I can verify this. So the identity is of course almost there. We have it here. Then we have a twofold axis in 1/8Y0, which is here. We have a glide plane A in XY0, which I have here. We have a glide plane B, which is here. The translation of 1/2, 0, 0. The twofold axis in 3/8Y0, where is it? It's here. A mirror plane in XY0. And a glide plane B in 1/8YZ. So you just confirmed that the transformation is correct. We have a subgroup of our PBAM space group. And by looking at the operators which have actually survived this transformation, that would be number 1, number 3, number 6, and number 8. Since the order is exactly the same, I can compare it to the international tables. And you can see here the subgroups. Operators 1, 3, 6, and 8 would be subgroup PMC21. So you directly have the symmetry of your crystal structure. So we just confirmed that the transformation is correct. Now we want to use this symmetry in our example. So I come to preview and I say transfer magnetic space group. And now this happens. Well, that can't be right, obviously, If something like this happens, don't panic. You can also always click Reset Symmetry to come back to your initial structure. So now let's see what went wrong. Well, as I said, we are using PBAM in a different setting. We doubled the lattice along the A direction. So we should tell the program that. Convert lattice constants. Now we have a cell which is doubled, but still something is wrong. The atoms are not where they should be. And this is also normal because the atomic positions which I had originally refer to the older small cell, but for the bigger cell, the X positions should be different. So I have to tell the program, convert atomic positions. Now we're getting closer. At least I have these tetrahedra, but I'm missing a lot of atoms. And this is also normal because, as I just found out, I'm using a subgroup of PBAM. So there are not enough operators to generate all the atomic positions. So I have to create split sites for some of these atomic sites here. So I say split sites in subgroup. And now if I transfer the magnetic space group, I have the same picture, but I have a doubled unit cell along A. And now I can actually verify which are the split sites. So those are the two different gadolinium sites, which in principle are not symmetry related anymore. I can play around with the oxygen positions. Yeah, looks like stretching exercises for octahedra. I could play with this all day long, but you maybe don't want to witness this. So I can reset parameters and I can check the magnetic structures, the magnetic degrees of freedom, just by playing around with these sliders. And one of these combinations will actually be the true magnetic structure of this compound. I don't remember it, of course, but I remember it's in the AB plane. So this component here is 0, but one of these combinations will be the right one. But you could use this as a starting point for the refinement of your structure. Short comment on magnetic superspace groups. Well, first of all, if you want to accept this, you can just close the window, then you have everything you need in the main window. And now a short comment on magnetic superspace groups. I won't show you a detailed example. You find that in the manual, but it works in exactly the same way. You can choose your magnetic space groups from a very long list here. And by the way, the information about magnetic space groups and superspace groups is based on the work of Stokes and co-worker of the isotropy suit. So if you use any of these details in your work, please cite these papers accordingly. Okay, so you can choose space groups here, superspace groups, and by working together with the isotropy suit, where you can load CIF files and you can enter the propagation vector, you can choose between different models, then the only thing you need to do is use either the numerical label or the space group label, enter it here. So you get the operators of this space group, including this internal variable tau. And you can use the basis transformation, which you have to read in column vectors. So you would have to enter 0, 0, -1 here, and then 0, 1, 0, 0, and so on. So it works in exactly the same way. You transform your magnetic superspace group and you apply it. Okay, questions?
There is no question in the chat for now. Yeah.
Okay.
We just have a compliment from Marcos, who is very impressed by your IREPS options.
Right, so it's nice to hear. I tried really hard to make things as easily understandable as possible. So if you are not very experienced with these rather complex things, that you can very easily apply them at least. Okay, so that was the introduction of magnetic symmetry into your example, into the structure files you would like to work with. Now let's move on to some single crystal related stuff. And I will open another example. It's not very important which structure it is. It's just something which we have measured many years ago on the D10 single crystal diffractometer. And if you want to use Mag2Pol with all its features in single crystal mode, the program needs to know a few things. So first thing, which instrument was it measured on? You can choose between different ILL single crystals, but you can also create your custom single crystal diffractometer with all these different input choices. And all of that is important in order to have an orientation matrix, which gives you the orientation of the sample within the diffractometer, and to know exactly how it is positioned for each and every HKL reflection you can measure. So this is the first thing. So this was measured on D10. The second thing, I need to input the orientation matrix. You can do it by hand, which I have already done here. You can also load the positions of some observed peaks to calculate it, but you can also type, this is rather on the preparation of an experiment. You can say, how would my orientation matrix look like if I put the A-axis vertical and the B-axis in plane? So that could be the orientation matrix. You can do some calculations if you want. You can play with the offsets and see how that affects the orientation matrix. So we'll cancel this because I don't want to overwrite these values. So first thing you can do is you can type some random HKL reflection, click go. So we've seen that last week. You can calculate nuclear and magnetic structure factors, but the program will also calculate the diffractometer angles, how the angles and motors have been rotated to put your single crystal in diffraction position. And this is important to know if you want to do an absorption correction, because you need to know how the neutron beam goes through your crystal, because you could have a very anisotropic sample shape where for one HKL reflection, there is very much, a long beam path inside the sample, and there may be other reflections where the beam path is very short. So you need to know that in order to do a precise absorption correction. And this can be done very nicely with Mag2Pol. And there are two different ways to do it. The nice way is if you have a series of pictures of your single crystal, which you can use to create your model. So I go to sample info here, this icon, where you have some basic information of your structure, magnetic structure, if I had one. And here I go to absorption. It will tell you the linear absorption coefficient, which is calculated based on your structure. And now I can define a crystal by clicking edit. So this opens a new window. And here I can load pictures which I have taken from my single crystal on the instrument after I have determined the orientation matrix. And before loading those pictures, I need to tell the program a few things. I need to tell it how the crystal was oriented, from where to where I have done the rotation, and what the perspective of the camera is. So all these information are quite well described in the manual. So if you want to do this, have a look. And now I will load the crystal frames. So those are the pictures which correspond to a full 360 rotation of my crystal. Here I have it. And I can go through them, and that's already quite nice. If your aspect ratio is not exactly as it is, if your picture does not have the same aspect ratio as this window, I recommend you to right-click somewhere in the picture and say adjust size. This is important so the program really knows where your mouse is moving. So you can rotate your crystal like this now. You can go frame by frame. You can click play, and you can click play with the loop. Do it faster and slower. And now the work starts. First thing I see is my crystal is not centered and my sample pin is crooked here. So of course the sample was centered in the diffractometer, but the camera which we placed afterwards was not necessarily well calibrated. So I have to do this, or I can do this in the program. So first, I come to offsets here, and I will rotate this picture. And then if you have ever tried to align a single crystal in a Eulerian cradle, You may remember that there are some strategies to get that done very quickly. And here you have some convenient shortcuts for rotations of 180 and 90 degrees, which I will use now. So I will compare the different positions, and I see that I have to move the camera a little bit. And now I have to move the sample by quite a lot, more or less like this. So it's already a little bit better. And now I do the other axis by rotating my 90 degrees, and I bring the sample more or less to the center. It doesn't have to be perfect, but at least now the sample stays in the crosshair. I can change the height also. Maybe there's a better perspective here. Yes, that's more or less okay. That should work. Next step is I have to tell the program that what the dimensions of my crystal is, because it does not know if this is 5 millimeters, 5 centimeters, or 5 meters. So I go to view, and now I need to know, of course, a real dimension of the crystal. Let's say, hypothetically, I know that from here to this border, it's 3 millimeters. Then I would say, then I would set 3 millimeters here, and I would adjust the zoom so that the crosshair matches this real dimension I know. And now the program knows about the size of the crystal. And now the fun can start. I can draw a 3D model of my sample, and I have to do that by introducing delimiting faces or planes of my crystal. This one, for example. So what is the easiest way to draw a face or a plane? It's by rotating it in a way that you see it as a line. And if it's a line, I can draw it very easily like this. And this is transformed directly into HKL values and a distance. And I will draw some other lines here to capture the first planes. Now I rotate the crystal. You see there are some planes, but they are not connected yet because I'm missing a roof and a floor, like this. And now I have a first model to start with in which I can refine. First thing I see, maybe I didn't draw this plane very well. I'm actually cutting away some parts of the crystal. So conveniently, I can just click a plane. It will tell me which one it is. So, and then I can click one of these parameters, and I can modify it like this. I can even click HK or L. This one is the correct one, so I will rotate it a little bit and bring it closer to the model, like this. And now I can start to shape my model a little bit better. Well, there are more simple and more complicated cases. This is a quite complicated one. So now you see, here we have a plane which is actually not needed anymore because it's outside of my model. And you can see it here in the list. It's not used anymore. So I can just right click, delete it. Yeah, I'll try to do this as quick as I can. So I just misclicked here. So I delete the last planes. I think this was wrong as well. So try again. Here, there's a lot of volume, which is not true. There's a big chunk over here. Maybe here, but it doesn't need to be perfect. You have more time than me to do it on your own, but this doesn't look too bad. So I can play this. I can also uncheck this option so I can see the whole model, or I hide the planes behind the picture, or I hide the crystal model at all so I can see my pictures better, but this doesn't look too bad. So I will use this. And if I click OK, I'm back here and I have 19 planes, which I've used to describe my single crystal to use it for absorption correction. And the cool thing now is if I go back to the orientation matrix window, I can see my 3D model, how it would be oriented in the diffractometer. So I can plot different objects like the Boosing-Levy frame. the direct axis of my sample or the reciprocal axis. I can remove edges or faces. This is up to you. And then there's this animate checkbox, which is a nice feature. So now if I calculate the HKL reflection and I say go, it will show me how it was actually rotated on the diffractometer to put it in reflection conditions. So the neutrons come from here and they're diffracted to the left, like it's the case on D10. And you can play with the angles to understand how your single crystal is actually rotated on the instrument. Okay. Any questions? Apart from this is very cool, thank you very much. nice comment. So if there are no questions, I would go on to the case where you can draw your crystal without having these pictures, because not everyone is in the comfortable position to have those. So I will load another example, which we can use afterwards for treating real data. I'm loading a ZIP file from a structure you know already from last week. It's this cobalt vanadate, but this time with doped nickel. So we have a statistical occupation of cobalt and nickel on the same Wyckoff sites, which is shown here by half and half colors on those spheres. And I will make it a little bit faster now. I will load an XML file where I have changed the colors, where I've put some polyhedra, as I've shown you last week. I have told the program that this was data taken on D10, and I have introduced the orientation matrix, which we have derived before starting the experiment. And now I want to draw my crystal model, but I don't have any pictures. Well, that doesn't matter. I just do the same thing. I edit my crystal, but I don't load any crystal frames. I just do as if I would draw a crystal on a picture. I rotate by more or less 90 degrees. The strategy is in the manual, so you can, strategy is a big word for this. I draw the roof and the floor, and now I have my dummy single crystal. And in my case, I knew that the crystal was cut along the principal directions, along A, B, and C, and I have measured those dimensions. So I can come here to the table and modify it by hand. I take the planes which are closest to the ones I know and correct them. Put a 1 here, 1, here I forgot a 0, 1, -1, -1, -1. And now I just have to look that up quickly. I measured that the crystal had an edge along the A-axis, which corresponded to 3.31 millimeters. So I divide that by 2 because each of the 100 and -100 planes will be separated from the origin by 1.655. Then I measured the B-axis to be 3.32. So that's 1.66 for those planes. And I have measured 3.72 for the C-axis, oops, divided by 2. So I enter 1.86 here. So that is a model of the single crystal I have used on D10 15 years ago. I accept that. And now I will start analyzing my data. So I go to the fit window, which you already know from last week, where we have loaded powder patterns on this side. But today we're loading single crystal data, integrated intensities, which will happen on that side. And there are different formats which are supported, either the int format, which you may know from FullProf, or you can directly load formats, which are the output files from integration programs, which run on the instruments. In this case, I will load a col file. So I will load the nuclear data collection at 2.4 angstrom. And the program will tell me there are 3 negative intensities, which I set to 0, because you will never be able to calculate a negative intensity. That doesn't make sense. So when I open this data reduction window, I have a list of all the reflections which have been measured, and they are classed or regrouped by equivalence. and the equivalents are according to the space group which you have entered here. You can try another one if you think it's not the correct one. It will directly give you the internal R value, which is a measure of the quality of your data collection. And it will give you some statistics, how many unique reflections, symmetry equivalent, and so on. In this case, we try to measure everything which respects the C-centering, but there are other forbidden reflections, but we've measured them anyway. You can choose to include them or not. I will not include them. Then you can order this table by any of these columns. You can even search for reflections by Command-Shift-F and say, did I measure the 040 reflection, because this was super important? So yes, I have it, so everything is fine. You can transform your HKL reflections if you want to switch to another setting of your structure, and you can do the absorption correction here. So you have to enter the wavelength. If it's not automatically entered, you have to put the linear absorption coefficient, but it's already calculated by the program, but you can modify it if you want. And then you can different types of corrections for spherical sample shapes, for cylindrical ones, that's where the radius is important. But for the special sample shape, we already have described our crystal here. And then you can set the grid. That's the number of integration points along the different directions. You can leave this with 10, 10, 10, that's fine. And now you can just click on apply. It will do the absorption correction. All the intensities are corrected. You have a different internal R value, which is almost the same. So don't get demotivated if you don't improve that by a lot. What really counts is the refinement quality of your structure refinement. It's not always the case that you improve the R int. So what else? You can click the HKL indices here to see the crystal in diffraction position. It will give you the beam path of the neutrons when going into the crystal and coming out, and it will give you the transmission factor for every reflection. And you can also see the distribution of integration points. You can compare your results. Here I have in blue the uncorrected data, and in red the corrected one. And in green, it's just the blue points, but normalized to the strongest reflection. So now I can compare red and green, and I see, well, maybe for this case, it was not absolutely necessary to do an absorption correction, but it's not so complicated, and it's the least you can do with single crystal data. So I can accept this. This would transfer these intensities to the fit window, or I can export it into a new file. This is what I've done beforehand. So I will load these files as in int format. So I have the data collection at 2.36 angstroms. And since we knew that there are strong extinction effects in our single crystals, we measured it at a second wavelength, 1.26, because extinction is wavelength dependent, and having two wavelength data set, it makes it possible to refine those corrections in a very stable way. I will click refine nuclear structure because this is what I want. This will add an atoms tab here. I could tell the program that I've loaded purely magnetic scattering. This is convenient if you don't want to change your input structure. You can just click it here and the program will ignore nuclear structure factors in the calculation. And there's a nice option which I called on-the-fly absorption correction. So what this does is it doesn't correct your data set, but it takes into account the absorption when calculating the intensities. This is very useful if you have a strong absorber, but you're not sure about the occupation. For example, you have 5% of natural gadolinium, or you have 6%. Well, those are the uncertainties that sometimes you don't know after the single crystal synthesis, but it makes a huge difference for the linear absorption coefficient. And with this option, you can actually refine the gadolinium content. And for every iteration in the refinement, the linear absorption coefficient will be recalculated based on the refined occupation. So I don't think you can do this with any other program. But we don't need this for this example. We will start the refinement now. I will refine scale factors for each of the data sets because I don't know how, I mean, the program doesn't know how long I have measured and how big my crystal was. So this is taken care of by the scale factor. Doesn't look very good. So I'm plotting calculated intensities versus observed. So ideally, they should all be on this straight line, which they are not yet. You can show your data as a function of sinus theta over lambda over peak number. I will state like this. And as I said before, there are strong extinction effects in the crystals I have used in my PhD thesis. So I will refine the diagonal of this extinction correction tensor. Look at the manual for more details if you're interested in and want to understand what it does. And now that looks already much better. I have R values of 8 point something, 7.9, which is already quite okay, but I haven't touched the structure yet. So I will want to refine the isotropic temperature factor of cobalt, and I will constrain the one of nickel to be the same because they're sharing the same site. So I think that's a reasonable assumption. I will do the same for the second site. So I will constrain B to the one of cobalt, but the second site also has a free Y component, which I want to refine, and I want nickel to follow this position. Now for the occupation, I'm not sure if the single crystal growth was perfect. I don't know if it's exactly 50-50%. So I will want to refine the occupation. But now if this value increases, I want this one to decrease because the sum should stay 1. So this I have to do under the constraints tab. And I would say atom 2 occupation is 1 minus atom 1 occupation. And the same for the second side. Atom 4 occupation is 1 minus atom 3 occupation. And you can actually check directly if your constraints are correct. You can change those values and see if the constraint values are correctly synchronized, which they are in this case. I will refine this. I won't touch vanadium because I cannot extract any information on that using neutron diffraction. I will refine the atomic position of the oxygen, and I will constrain the temperature factor to be the same for all the oxygen atoms. And now I click hit. So visually, not much happened, but we went down in R factors to 4.5 and 3.3, which is a very good result. And I also see that I have reasonable temperature factors, which are positive, which is always good. And I have, which I can see better here maybe, I have a preferential occupation of cobalt on the first side, then on the second side. I saw that systematically on my samples, no idea why. But that's all we can do for the moment. So I accept this refinement because this was actually just the groundwork for the stuff we were actually interested in. We wanted to deduce the magnetic structure of this compound. So this is the usual way of working. First, you refine your nuclear structure, so you have an idea how to scale the magnetic intensities. So that was the first step. Now we'll take the program. I will tell the program, actually, I have magnetic ions, and they are in oxidation state 2+. So the program knows which magnetic form factor to use. I regenerate this. Now I will right-click here because I only want to see the magnetic ions, and I will change. I will remove the polyhedra, and I will draw bonds between cobalt and cobalt with a gradient. So now I just quickly changed between the view on the structural details to the magnetic lattice. And by looking at this, you directly understand why in the literature, this is called the cross-tie site, and this is called the spine site. And now I want to use magnetic symmetries from irreducible representations. So I go to the spins tab, I enter the propagation vector, I regenerate, so everything is saved. And this was really 0.49. We made sure this is not 0.5 because this would actually make a difference for the symmetry. So now I click on the IREPs button, which will calculate the different IREPs. And I see for the first site, I have 4 different IREPs with up to 2 basis vectors. And for the second site, I have up to 3 basis vectors. So I'll set random values here just to visualize the structures. And I will say use gamma 1. By the way, I forgot to say before, you can even combine representations if you just highlight 2 of them and right click, and then you can use a combination of both. Now, what we see in this case is that we have a fully ordered moment along one direction, then a 0 amplitude, a fully ordered moment in the other direction, again, 0 amplitude. This is not very physical, but we can easily change that by applying a global phase factor to all the ions, which doesn't change the symmetry, which doesn't change the intensities we calculate. It just does make more sense. So this could be one magnetic structure, but we can have also different symmetries, and I can click through them like this. So let's try the first one. So I will go into the fit window. Now I still have my old nuclear structure data, which I don't want to use, but in the case of the magnetic structure, I only measured intensities at 2.36. So I will remove this part, which will take away the scale factor of the second data set, but I want to keep the scale factor of the 2.36 data collection, because I used exactly the same counting time, the same single crystal, so the scale factor has to be the same. So I right click and say replace, and I use the data with the magnetic intensities. And you see the scale factor is conserved. And now, actually, I don't really want to refine the nuclear structure anymore. So I remove that. And the program is nice enough to tell me that there is a problem with the constraints, but I don't have any occupations anymore because I removed all the atomic parameters. So I remove the constraints. And now I fit the magnetic moments. And I will brute force it. I will just refine everything which is symmetrically allowed. But I will constrain the moments, the magnetic moments of nickel to be the same as the ones on cobalt, because they're sharing the same site. And actually I cannot really extract if they are behaving differently. I get the global magnetic structure. And I refine the 3 basis vectors for the second site. And again, I constrain the moments to be the same. And now I fit. Looks horrible. That's okay. It just means that the model is probably not correct. Don't worry about the NANs here. This is because the first model only has 1 basis vector. So it doesn't really make sense to refine something which is 0, but it does the fit anyway. And now the cool thing is I don't need to change anything. I just use gamma 2 and click on fit again, and it will try the second model. And now I click on gamma 3 and it will try the third model, which looks like a success here. But just to make sure, I will try gamma 4 as well. Doesn't work. Okay, so in no time, I cycled through the different IREPs and made the fit against the data very quickly. Now I can inspect my results. So I have a R value of 13.3, which is acceptable for a magnetic structure refinement. And even I didn't even average the reflections because I didn't know to which symmetry to average them. And I have results, which I will inspect now. So I have a coefficient which is 0 because the error bar is bigger than the refined value. So I can set them to 0. And probably this one is not really significant as well. So I will set this to 0, not refine it anymore, like this. And let's compare. We go from 13.29 in R to 13.35. Okay, almost no change. So that's it. We found the magnetic structure of this compound. So I accept this. And I can look at my magnetic structure. And this is what I have done in another file. I will just open this. And I will put on the guide to the eye again. So we interpreted at the time that we have a funny structure where we have kind of loops of spins circling around and like waves going around here. So the interpretation is another thing that's up to you. But we found a solution. And now you have to imagine young me in 2007, super happy with the results. I go to see Bashir. Bashir is the instrument responsible of D10. And I tell him, Bashir, look, we have nice results. There are 4 models. There's only one which works. So I show him. And he smiles at me and says, yeah, that looks so good. I almost no need to check it, do I? So I say, no, you can trust me. This is correct. So I'm even happier. So the next day I call my supervisor in Germany and tell him, good news, we got the magnetic structure of this cobalt nickel compound. And he goes, well, that's great, Navid, but have you checked the model against your old D1A data? And did you do a correlated refinement? And on the inside, I was like, no, please don't make me do this. The results are so nice. Let's publish it like this. Because of course I knew that's a lot of work again. And if the models don't match between the 2 data sets, I'm in big trouble because I already sold that as the ultimate solution. So what followed was a huge fight of copy pasting between different input and example files until I finally got the program to work, which I used 15 years ago. But if I had had Mag2Pol at that time, I could have told him, wait a minute, I will tell you. So I would open the fit window again, look at my last fit, which was here. And now I just add my D1A data. And this part, you know, from last week, I go to the patterns tab. Under geometry, I use D1A medium resolution, which was the case at that time. I remove the parts which I'm not interested in and only plot that part, 0.2. I give the program some background points. Doesn't have to be super precise. That should be okay. Then I manually change some parameters which I see which are completely off. So the scale is too high, so that already looks better. I will refine the background points, the zero shift, the scale factor, and the lattice constants. And nothing happens. That's normal because now I have the option to change the weight between the different data sets. And for the moment, it's fully on the intensities. So it doesn't take into account the powder data. So now I can grab this dot and drag it around, and it conveniently snaps in and 1/2. That's where I would let it. If I would load polarimetry data, I could actually drag this dot over this whole weight triangle. And now I fit again. And now I see both data sets, and I can see how the powder, the calculated pattern gets better and better. I will add the resolution parameters to the fit. And this peak intensities became better now. Yes, so now I could tell you, well, it looks very, very good, but that's only half of the truth because, and that's another convenient thing with Mag2Pol, you don't need to change anything on the structure. You don't need to change your input parameters. You can just decide what you want to include in the fit. Do you want to include the magnetic and or the nuclear contribution? So if I remove magnetic, you see it's actually here only where the magnetic scattering is concentrated. So I will zoom on this part. And now we see, even though they are small, the calculated pattern based on the magnetic structure actually describes everything very well. But we can fine tune it, of course. I can refine the component of the propagation vector. And I can also think of an eventual broadening of the magnetic peaks. So you have these delta values, which are only applied to magnetic peaks. So I could refine this. And now conveniently in the fit window, it will concentrate on the last view I had in the patterns tab. So we see the propagation vector was in fact not 1/2, it's smaller than that. And well, maybe, well, here's a little problem. Maybe I can fix that with the asymmetry like I did last week. I will refine this parameter. And bingo, everything looks very, very nice. So yes, I hope I could convince you that with Mag2Pol, it's very, very easy to co-refine different data sets. So we use different two wavelengths for the nuclear part, then we combine it with powder data. We have a super easy way to input magnetic symmetries. And I hope that this can be useful for you in the future. So with this, I would conclude this the second part of the courses.